Welcome back, reinforcement learning. This session I explained comparing the probability distributions. Okay, distributional Q learning concept we are discussed from last sessions. In distributed Q learning, we got the distributional value. Generally, Q learning generate the estimated rewards, estimated deterministic values, but in distributed Q learning we got the distributional rewards, distributional values. So in distributional values, in comparing the distributional probability distributions, okay, in comparing the probability distributions we are required in evaluate the distributed Q learning concept, distributed Q learning applications. Okay, we are applied the distributional Q learning, distributed deep Q learnings on different applications. How to evaluate the distributed Q learning on applications? By using by comparing the predicted values and actual values. We calculate the differences between estimated values and actual values. So that both are the probability distributed values. So we have to compare the actual probability distribution values and predicted distributional values. General compare values are we are using loss values. We are generally using loss values are not suitable to compare the probability distributional values. So for that we are used different algorithms. Before that we see the generative models and empirical models. Okay, in generative models means aim to learn the underlying distribution of data sets so that they can generate the new samples that are similar to the training data, that is the generative models. For instance, a generative model trained on celebrity images would learn to produce the new images that resemble those in the training set. So that the generative models similar to the training data. In empirical data set versus generative data, the empirical data refers to the real world data collected from observations, while generative data is produced by the generative models. So empirical data refers to the real world data, the generative data generated by the models. The objective of training a generative model is to maximize the likelihood that the generated data closely matches to the empirical data. So we are generated distributed deep Q learning produce the probability distribution values, generated probability distribution values. Those are very compared those values with the empirical distributional values. So we are using target distribution generation. Targeted distribution generation is generated by get underscore target dist function in PyTorch. Okay, this generate the target distribution for the reinforcement learning task based on the observed rewards and prior distributions. The terminal states with specific rewards, okay, terminal state means ending state, produce the degenerative distributions, while non-terminal states use Bayesian updates for distribution. The terminal states produce the degenerate distributions, non-terminal states use the Bayesian updates for distributions. So we compare the both empirical distribution and generative distributions. So our general loss functions are not suitable for to compare the probability distribution values. The general loss functions, the mean squared error, root mean square errors, these are not suitable for our compare the probability distribution values. So we need compare the probability distribution values by using Kullback-Leibel divergence or cross entropy loss. We are using KL divergence or cross entropy loss to compare the probability distributions. The Kullback-Leibel divergence, KL divergence, is a measure of how the probability distribution diverges from a second expected probability distribution. It quantifies the difference between two distributions. It is compared the two distributions denoted the DKL, okay, Q compared with the P. So the where Q is the true distribution, P is the model distribution. Q is the empirical distribution, P is the generative distribution, or Q is the actual distribution, P is the model generated distribution. We compare the Q and P with KL divergence or cross entropy. The KL divergence is defined mathematically using the formula sigma x q of x log probability of x p of x into q of x. X is the instance or sample, p is the model generated data sample, q is the actual sample, x is the sample. So using this formula we calculate cross entropy or KL divergence value. The lower KL divergence, any loss is minimum loss is the best model. So the lower KL divergence indicates that the two distributions are more similar. So the loss is less means they are related, very close related. So while the higher value indicates greater divergence. So divergence is minimum with the low loss values. The divergence is high means the loss value is very high. We are using KL divergence to compare the two probability distributions, measure the difference between the two probability distributions, the P of x and the Q of x data. They are it is a not symmetric model, means comparison with P and Q is not equal to comparison between Q and P, and simplified to cross entropy when only optimizing the model generated distributions. This is the KL. The cross entropy we already seen the both are same. Qx is the empirical distribution and Px is the model generated distribution. Optimizes the alignment of the models predictions with the true data distributions. The optimization means both are very close values. So implementation in neural networks, models such as the distributed DQN use the cross entropy to update the action value distributions. We train the models based on the entropy loss value. The distributional approaches allow capturing the uncertainty and variability in predictions. This is the code to generate the comparison between the distribution probability distributions. The previous example code we are using the some example. It has the support values and number of epochs, number of samples. Okay, in the previous example, loss is calculated by using this one. Generate the target distribution using this code. We are calculating the KL divergence using this code, PyTorch code, and cross entropy and practical applications. We are using the comparing the probability distributions in reinforcement learning to compare the probability distribution of the distributional DQN models and generative models. The compare with the generative models, GAN such type of models and VAE type of models to predicted and generative models and simulate the testing. We are using the probability distributions, the synthetic data and predefined parameters means generated data and model data we are compared with simulated data testing. Okay, and challenges and considerations is numerical stability, direct multiplication of the probabilities risk numerical underflow using the log probabilities avoid this issue, and weighting samples. Real world samples may have the different probabilities. Weighted loss function can address this variability, and symmetry. Loss functions like KL divergence are directional and choosing the DKL or DKL QRP or PRQ depends on the use case. Okay, this is the symmetry. So these are the challenges in the numerical stability is solved by using log probabilities and weighted samples. Different weighted samples we are solved by using by addressing the one variability, and symmetry we can loss functions KL are directional. So it is directional. Both are DKL of QRP is not equal to DKL of P and Q. So we are choosing the direction depend on our use cases. Okay, thank you.